Welcome to Data Lab. This sequel will show you how to perform simple linear regression using a PINA data lab. For that purpose, we load an interesting dataset obtained from the NOAA Greenhouse Gas Monitoring Program. Besides the well-known carbon dioxide and methane, there are several other greenhouse gases which have received increased attention. One of these greenhouse gases is sulfur hexafluoride, SF6, which is extremely potent and has a warming potential of 24,000 times that of carbon dioxide. So here we have the dataset measured by the National Oceanic and Atmospheric Administration on Mauna Loa in Hawaii over several decades. Though the concentration of the gas is currently quite low, around 10 ppt, which means parts per trillion, it is increasing from year to year, and it seems to increase not linearly but quadratically, which means that the emissions of SF6 are linearly increasing every year. So the question we want to answer is, what will the concentration of SF6 be in 5 and in 10 years from now, assuming the emissions keep rising from year to year as of August 2021? If we look at the data, we see that the x-axis shows incomprehensible numbers instead of years. The reason for this lies in the fact that the date is encoded in a format which counts the number of days since December 30th, 1899. Data Lab provides the easy conversion from this format into a readable date. We simply have to select the date-time format for the x-axis. The data basically shows two unwanted effects, which we should correct in order to establish a usable regression model. First, at the beginning of the measurement series, there might have been a problem with the calibration of the instruments. Second, obviously there are several outliers in the dataset. Both of these effects will adversely influence the regression model. Thus, we have to get rid of these data points, and the simplest way to do that is to mark the data points and use the command edit, data, delete, marked rows. So let's do that. Now that we have arrived at a data set which has been cleared of the most problematic measurements, we can try to establish a regression model for the SF6 concentration over time. For that purpose, we open the linear regression tool by clicking this button here. We now have to select the independent variable, which is the time in our case, and the dependent variable, which is the SF6 concentration. If we set up a linear model, which is the default case in this tool, we immediately see that the linear model does not fit too well. By looking at the residuals, we could conclude that the model is indeed quadratic, as the residuals show a roughly parabolic form. So let's select a parabolic model. This shows a much better fit, though the residuals show some structure which may point to problems with the instrumentation. Don't forget that the SF6 concentration is extremely low, and a change of the instrumental setup certainly has a slight effect on the acquired data. The estimated regression function can be seen on the Details tab. You see here the general function, in our case a polynomial of second order, and below the estimated parameters. At the bottom of the report, we find the results from the ANOVA, which indicate that the model is highly significant and valid. When creating a regression model, we have to check for the assumptions of ordinary least squares. These assumptions can be checked by analyzing the residuals. The residuals should be normally distributed and homoscedastic, and there should be no autocorrelation. First of all, we check whether the residuals are normally distributed. Looking at the distribution of the residuals indicates a slight deviation from the normal distribution, which is indeed confirmed by the corresponding test for normality in the details section. Next, we look for homoscedasticity. The residual plot shows a slight increase of the variance towards higher SF6 concentrations. And again, this is confirmed by the corresponding statistical test. Finally, we check whether there is serial correlation in the residuals by performing a Durbin-Watson test. This test indicates a clear serial correlation. So obviously the assumptions for the regression model are not met by the selected model, which might indicate that the simple quadratic model we have selected does not accurately represent the underlying trend in the data. While the model obviously fits quite well, we should be careful when using this model for a forecast of the SF6 concentration too far into the future. As our data covers roughly 20 years, we should not extrapolate the model more than maybe 5 to 10 years into the future. So let's try to estimate the SF6 concentration for August 2026. We therefore select the tab Calculate. In this field, we can enter the X value for which the concentration should be estimated. Remember that the X values are encoded as the number of days since December 30th, 1899. To be able to conveniently enter the intended date, we can use the built-in calendar function. When we click the Calculate button, DataLab applies the regression model to the intended date, delivering an estimate of the SF6 concentration for August 2026. The estimated value is accompanied by its confidence interval at the preselected confidence level. Thus, the estimated value y hat for August 2026 is 12.99 plus or minus 0.14 ppt. Repeating the same process for August 2031 results in 15.28 plus or minus 0.14 ppt. Well, that's all for now. Visit the DataLab channel on YouTube for more examples on how to work with DataLab. Stay tuned.